All right, we are now on chapter 13. This is, I think, when it kind of gets fun, although it's been fun this whole time, but kinetics is a very fun chapter to kind of think about. We've been talking about reactions, but what's really going on? What's the mechanism involved? What's the steps going from reactants to products, and how do we influence that and change it so it goes faster or slower? So we're going to be looking at chemical reactions in terms of what's actually going on a little bit. This is going to be talking about chemical kinetics. All right, this whole chapter is the study of how chemical reactions rates change. I just made that little rates get bigger here. Let's just talk about that word a little bit, rate. Okay, so you are familiar. If I asked you about rates of things, you probably could tell me. So let's say, for example, I pay a babysitter to come over and watch some of my children, sometimes especially in the morning when I have to come in and teach. I will pay a certain rate, and that's usually, dollars per hour, right? If you have a job, you are familiar with that. Now, I will change my rate because sometimes I make the babysitters come in really early. If I want to go work out in the morning before coming to teach, I might make the babysitters come in at 6 o'clock in the morning. And now, if you make a babysitter come, this is a college student usually, come at 6 in the morning to someone's house, you might need to encourage them by paying them a little bit more. And sometimes I also will have my babysitters help with laundry and other things. So if I'm going to have them do chores, I pay them a little bit more. So I increase the rate depending on the job that they need to do. Other rates, let's see, speed, okay. If you guys are driving cars, a lot of you are maybe getting your driver's license soon, or you have your driver's license, and your parents probably are very concerned with the rate that you are driving. Now, you will hopefully stay within the speeding limits, okay, for the rate, and that's usually in miles per hour. But you can change your rate depending on where you are. If you're on a highway, you would go at a faster rate than you are driving through town. Another rate is metronome, okay? So if you play the piano at all, you might need to count how many beats per minute that you are playing, and you can increase that or decrease that depending on what the song requires. So these are all some of the rates that you might be familiar with. We're going to be looking in this whole chapter about how we can increase or decrease the rates of chemical reactions and what that means. All right, so when we're talking about the rates, we have to talk a little bit about the reaction itself. All right, so the reaction is a sequence of steps that the molecule would undergo when going from reactants to products. So far, we've just written down reactions and said, oh, here's the reactants, here's the products, and voila, they're done. Now, it doesn't often happen just in one step. There might be several steps that have to occur. Okay, if you have done the synthesis of aspirin, okay, making acetylsalicylic acid from salicylic acid, your instructor might have led you through some of those steps involving kind of the sequence of, hey, what happens first to change these functional groups between salicylic and acetylsalicylic acid. So let's look at this example here. So we have methane, CH4 is reacting with oxygen, making carbon dioxide and water. What type of reaction is this? You should be able to say, hey, that's a combustion reaction. So we're going to combust methane gas. Now, if you look at it, we have a carbon with 4 hydrogen bonds, okay, tetrahedral in its shape there. And then we have 2 oxygen molecules. Each of them have 2 oxygen atoms with a double bond between them. All right, when you go to the other side, to the product side, do you see any CH bonds? No, all I see now are oxygen and hydrogen bonds, okay, making the water. Do you see any oxygen-oxygen double bonds? No, not on the product side. Now we have a carbon-oxygen double bond. So all of the bonds in the reactants have had to break apart, and then new bonds have had to form. Now, as far as the mechanism goes, okay, it is going to be very unlikely that 1 methane and 2 oxygen, so a total of 3 different molecules, all come together with enough energy, orientation, and at the same time and collide in order to break all of the bonds at the same time and then reform new ones. Okay, it will be more likely that this happens in a series of steps. All right, and so that would be the reaction mechanism that's going on. Let's just switch here. Before we talk a little bit more about that, I want to talk a little bit about rates in general. Now, oftentimes you're probably thinking, well, we want to increase the rate. We want to make it go faster. We live in a world that we want things smaller and faster and better. But if you think about reactions, there's sometimes where you want reactions to go fast and sometimes you want them to go slow. So in your car, you have a catalytic converter. It takes out the greenhouse gas. Okay, when you do a combustion, sometimes you have an incomplete combustion. You're making carbon monoxide and you're making some carbon dioxide. You want to kind of remove some of these greenhouse gases before they get into the atmosphere. And so you need this to turn over really fast. So that's a reaction you need to go quickly. When you are cooking food, you're usually hungry, and so you might be like, I want to eat really fast. So you want those reactions to get remember thinking about our pasta boiling? I might add some salt to my pasta so it boils at an even higher temperature so I don't even have to boil it as long. All right, but then you have the reactions taking place when you're digesting the food, and this takes a lot longer, okay? Why does it take longer? Why would we want that to take longer? And you might think, well, if it just goes through our body really fast, we're not going to absorb any of the nutrients and get the energy out of it that we could if it took longer. So that's a reaction that you might want to take longer. Understanding how drugs work. If you think about it, there's a lot of different drugs that you take and you swallow. There's some drugs that you take and it might be like with a needle, get it absorbed right into your blood. Why would some you want to take a lot longer to actually go through the reaction? Why would you want some fast? So I have allergies, okay, so seasonal allergies. I could take a pill every couple hours, okay, or I could take one that says 24 hours. And now that one would be a slow release one, okay? I'd probably rather take the one I only have to take once a day. And so that reaction, okay, they might have a couple layers that the first layer releases pretty quick, and then the other ones take time, so you have a constant rate of, or constant concentration of that drug in your system. Okay, so we might want some drugs to take a long time. Now, if you are having an allergic reaction to something, okay, and you have to take a pill and then wait for it to get dissolved and then wait for it to get to your bloodstream, that might be too late. All right, so if you have someone or know someone or you have an EpiPen, you need that pretty quickly if it depends on you being able to breathe. So you want those to react really quickly. So sometimes you want drugs fast, sometimes you want them to last over a long time. Decomposition of food, okay, the reactions involved in spoiling of food, you want to slow those reactions down. So oftentimes you can put them in the refrigerator or freezer, lower their temperature so the reactions don't go quite as fast. Also things like transportation, roads, bridges, things like that, buildings, you want those to last a long time. So the reactions involved in their oxidation of the metals or whatever, you don't want those to happen, so you try to add things to get them to slow down. All right, so that's kind of why we're studying reaction rates. Sometimes we want things to go fast, sometimes we want them to go slow, and we can then look at the field of kinetics to try to figure that out. All right, so you cannot actually observe individual atoms and molecules, okay, at their scale to see how they're going about changing from reactants to products. Some reactions have been observed very carefully and they might know a little bit more than others. But we can do things to kind of figure out, well, if I change the temperature, how will this speed up the reaction, okay? If I change the concentration of all the reactants, what happens? How if I just change the concentration of one reactant? What is the impact on the speed of the reaction? So these are some great labs to do. There's several of these that are common kinetic labs. Some great demonstrations to do also dealing with chemical kinetics. There's one more little picture here, okay, and this is trying just to show a common type of mechanism. It's called a substitution mechanism or reaction. So you have one thing kind of coming in, another thing on that molecule that it's coming into leaving. So it's substituting an atom or a group of atoms. This is very common in organic chemistry. If you go on in college up to higher level courses, you'll be looking at mechanisms, and a substitution one is one you'll hear about quite a bit. So you have an OH here. It needs to come in and collide with a ch13Br, and then you can see that the product then, the OH is joined up, and the Br minus has now left. Okay, so this would be a substitution reaction involving here, and the speed of this reaction will depend a little bit on the orientation and the energy of the reactants involved. All right, I think that should be good to get this one started. We'll look a little bit more at the energies involved in the next video.